In this video, we'd like to discuss a second way of solving equations of the form a cosine x plus b sine x equals c. And before you use c, cosine x plus 2 sine x equals 5 as the equation we want to consider. When you talked about solving trigonometric equations of this form before, what we typically think towards is the fact that cosine squared plus sine squared equals 1, so we know that we can use that Pythagorean identity to replace cosine as square root of 1 minus sine squared, or sine x as 1 minus cosine squared x. Or, in other words, that means we need to create squared terms so that we can replace them without the radicals. Let's look at a second way of solving this type of an equation. Consider the identity for, let's choose the sum of two angles with sine. And we could use sine of sum, sine of a difference, cosine of a sum, cosine of a difference. As long as it's cosine and sine, we can make one of those work. We know that this comes to be sine A cosine B plus cosine A sine B. We've got two angles, and notice that this expression contains both sine and cosine. It contains, in this particular identity, it contains also the cosine and sine of the same angle joined by an addition. So suppose we could recreate this, the right side of the identity, so that we could go back to sine of A plus B. Well, how on earth are we going to do that? Well, in much of the trig setting, and in particular when we talk about identities, we're used to seeing this type of thing where everything is expressed in terms of a visible sine, cosine, cosine, sine. But suppose we look at the coefficients here, the 1 cosine and the 2 sine, as actually being numerators for sine and cosine. The actual sine and cosine functions, in this case sine A cosine of A. Why do I say only the numerators? Well, we know that sine and cosine stays between -1 and +1, so this wouldn't serve as one of those functions. However, it does, we do have the ability of letting the 1 and the 2 here be sides of a right triangle. And we know that as long as we can figure out that third side, then we can find all of the functions of this particular angle that I'm going to call A. Well, we know how to do that. We know that this particular side right here is the hypotenuse, so 2 squared plus 1 squared, square root of that will give us that third side. Now, before we go any further, notice that up here we're referring to A, B, and C. And there's a danger to that when we're talking about this type of an equation, as opposed to a quadratic equation where you also see an A, B, and a C. In the quadratic equation, we don't have any problem with the fact that all three of those letters represent constants. But in this setting, especially when we draw that right triangle, we tend to want to think of C as being the hypotenuse here. But for the purposes of this generalized equation here, that C doesn't refer to a side of a right triangle, even though we're going to use the A and B to be sides of a right triangle. So keep that clear, and you might want to go so far as to say, call this side, say, R, like the radius of a circle, so that you don't confuse this with having to be 5. And in fact, if we do the 2 squared plus the 1 squared, we get 5. This would actually come out to be the square root of 5. So again, no mystery there. We're just using our Pythagorean theorem. R squared equals 1 squared plus 2 squared. And I'm not meaning to insult your intelligence here by writing out something that you probably were able to follow when I spoke it. I know from my years of teaching that it's always better to be safe than sorry and not leave a student in doubt as to where something came from. Now, what's the significance here? Well, if I want to recreate this identity form, well, I've got a cosine here. I need to multiply times the sine. And I've got a sine here. I need to multiply by cosine. Notice we also could use the cosine of a minus b, because it also has a plus sign. And then I'd need cosine times cosine and sine times sine. So we can generally use more than one of the addition identities. All that matters is that you go ahead and use one. So now that I know what my hypotenuse is, and I can tell myself, whether you write it down or not, that in this case the sine of A would be 2 over the square root of 5, and the cosine of A is equal to 1 over the square root of 5. So now we can say, all right, right here, since I want sine A, then I can put in the actual numerical value of sine of A. And then that means I've got sine of A times cosine X plus, now the cosine is 1 over square root of 5. And in order to be able to put that in, what did I actually have to do to this equation? Well, I had to divide everything by the square root of 5. Oops, I forgot to put in the sine x. So we end up with this new equation where, again, this is our sine of angle A, and we're just going to call it A for right now, and this is cosine X, and this is cosine angle A times sine X equals, let's go ahead and rationalize that. Get square root of 5, square root of 5. We get 5 times the square root of 5 over 5, and those will cancel. So we've got sine A cosine X plus cosine A sine X equals square root of 5. Now, I've established the pattern that I was interested in, the sine of a sum. So I can rewrite this as the sine of A plus X equals the square root of 5. And in a way, it's kind of nice to leave this a instead of putting in a numerical value for the angle, because when we see numbers, we tend to want to address them before we actually address functions. So this kind of saves us a mistake. We now know then that a plus x is going to be inverse cosine, or the inverse sine of the square root of 5. Now, what's that come out to be? If you punch your buttons real quickly, if you don't recognize before you punch the buttons, your answer, your calculator is going to say this. Why is it saying that? What's the square root of 5? How large is it? Is it larger than 1? Well, sure. Square root of 5 is larger than the square root of 4, which is 2. Obviously, if this equation comes out to sine of whatever angle is equal to square root of 5, we have no solution. It's not possible. Which means by going this route, I've saved myself a bunch of time over squaring both sides, because in squaring both sides, I get solutions that might look okay, but when I plug them back in, they won't check. And with the nature of the angles, we might tend to not check them anyhow. So by going here, we've created a situation where it's real obvious that this comes out not so good. But notice again what we did. We looked at this equation. We had the option of squaring both sides. We decided to look at the coefficients here as being sides of a right triangle that then allow us to find the third side, and then by dividing everything in the equation by that hypotenuse, recreate the sign of a sum in this case, which allows us to get rid of a whole bunch of function that we really don't want to have to deal with, and gives us this one simple little sine of an angle equals a constant. And at this point we can tell whether or not we're going to get a solution. If we get a solution, remember we have to look for values that are in quadrants where the sign is positive, so we get a solution in the first and a solution in the second. It's, in this case, larger than allowable for a sine, so we know we're done.